please welcome Varav Gandhi, Senior Program Manager, Windows and the Device Group, and Luke Angelini, Senior Program Manager, Windows and the Device Group. They will discuss transition to universal Windows drivers. Ladies and gentlemen, let's welcome Varav and Luke.
Well, hi everyone. Welcome to WinHEC, and thank you for attending our session. I wanted to reinforce the message we heard today at the keynote session and in the Windows 10s session about Windows being one of the most secure, personal, and up-to-date operating system. We at Microsoft truly believe that software drivers are the most important piece of code on a user's machine alongside the Windows operating system. The two in conjunction provide a delightful and an engaging and immersive end-to-end experience to our users. The importance of a well-written driver should not be underestimated. A well-written and an efficient driver easily allows a good piece of hardware to outperform a great piece of hardware any day. My name is Varav Gandhi. I am a program manager in the Windows Devices Group at Microsoft.
And my name's Luke Angelini. I'm a peer of Varav's. We're here today in beautiful Taipei to share with you, our most valued partners, Microsoft's plan to improve driver quality and OS upgrade resiliency by transitioning to universal Windows drivers. Throughout this presentation, we will highlight the important foundational aspects of universal Windows drivers and the benefits they accrue to you, our partners, as well as Microsoft. Let's get started.
All right, we have a pretty packed agenda today. We're first going to highlight the importance of universal drivers to the Windows ecosystem and the value proposition and benefits they provide. We will continue to highlight the core principles of authoring universal drivers that allow them to be cleanly installed, uninstalled, and be resilient to OS upgrade, which are happening very, very frequently with Windows 10. Finally, we will discuss timelines, roadmap, tools, documentation that allow you to adapt and transition to universal drivers starting right now. So to set context for this discussion, let's take a brief journey down memory lane. At the beginning of this decade, Microsoft had three primary products with widely divergent code base. In 2011, Microsoft and our hardware partners tried to put Windows on PCs, phones, and consoles, and the long-standing divergence in the underlying platform made it very costly to support all three platforms for both the hardware partners and Microsoft. Starting with Windows 10, we're building these three products and many more, all on a common code base that are shared by all Windows 10 products. This allows ISVs to easily bring their applications to the Windows Store, and it also allows IHVs and silicon vendors like yourself to easily adapt their components to multiple device families. With that, Windows 10 runs on a variety of form factors, starting from phones, desktops, two-in-ones, to giant screen devices like the Surface Hub, to embedded devices running IoT Core. At the heart of Windows 10 is one core OS. This includes kernel, networking, storage, and these components are common across all device families running Windows 10. This provides focus and increases Microsoft's ability to rapidly innovate and fix issues on the core OS and deploy these fixes across all Windows 10 family of devices. OS edition-specific features and functionality are added as optional packages on top of the core OS. This provides unique value adds specific to that OS edition to provide a delightful, engaging, and an end-to-end experience. Included in the in the One Core OS is a common app platform, which provides a consistent set of APIs that allows ISVs to write universal applications. We saw the build demo. The ISV community is very excited about writing universal apps. And these apps are designed to be written once, and they run across every single Windows 10 edition. Also included in One Core is a common device platform. This includes all the common set of DDIs across all device areas, and it provides the ability to our hardware partners to write universal Windows drivers. These drivers are designed to be written once and can be targeted to every single Windows 10 edition. Starting with Windows 10, Microsoft is releasing feature updates and quality fixes at a faster rate than ever before. We're releasing feature updates twice a year and quality fixes every month. So how do we build drivers so it's easy for our users to keep up with this pace of innovation? As I mentioned earlier, drivers are alongside the OS in terms of criticality and importance. We have to make it easy so driver issues are no longer the roadblock preventing Windows users from getting the latest OS features and updates twice a year. We want driver uninstalls and installs to be deterministic and clean. And we want a single core driver that works across all supported PCs that have that component or silicon, and servicing of add-ons such as applications and customizations is decoupled from it. Old ways of writing, testing, and servicing drivers makes it difficult and expensive for our hardware partners and for Microsoft to keep pace with the rapid pace of innovation and Windows release. There has to be a better way, and we believe that writing universal Windows driver are part of the answer. So universal Windows drivers are not only meant to run across all Windows 10 OS edition, but they are also designed and packaged to make them resilient to installs, uninstalls, and frequent OS and driver updates. Writing universal drivers is easier than ever before because the WDK integrates with the very familiar Visual Studio toolset, which is on thousands and millions of machines across the world. It makes it easy, or writing universal drivers makes it possible for IHVs to cross-sell their components to OEMs and ODMs that are building devices with any Windows 10 operating system. For the next half an hour to 45 minutes, we are going to deep dive on the universal driver pillars. So let's spend some time on these 4 foundational pillars for universal Windows drivers. We want universal drivers to be declaratively installed. If your driver has OEM-specific settings or there are some driver customizations, we want them to be separated outside the core driver, which allows your core driver to run everywhere. If your driver or if your hardware has a companion app, we want that application to be converted to a UWP app and be serviced from the store. And finally, we want your drivers to only access universal APIs. This allows you to sell your components into any OEM that's manufacturing devices targeting Win 10 OS editions. We will hear terms like D, C, H, U, and for your reference, this is what we are talking about: declarative, componentized, hardware support apps, and universal APIs. So let's double-click on this more, and I'll hand it over to Luke to start off with the declarative part.
Thank you, Varaf. So the first pillar we're going to talk about today is declarative. Declarative is making your driver installable with nothing more than an INF. Why do we care about declarative drivers? As we've entered this world of Windows 10, We've upgraded millions and millions of machines. And through this process, we found that if Windows doesn't have the ability to know exactly what's necessary for the driver to run and install, it makes it very difficult for us to be able to maintain that driver and upgrade it month over month. And so we found that having unknown runtime operations leads to fragile updates and unknown states after upgrade. By having a declarative installation, we're able to very precisely know exactly what needs to be installed and uninstalled. And so we can maintain these drivers much, much more easily. It allows us to stay current much more easily. It reduces support cost, and it aligns with all the requirements for all our new OS additions. So how do we make our drivers declarative, right? It's great to say it. It sounds awesome, but what does it mean? All drivers on Windows need to be installed using an INF. This INF has to be the only thing necessary to get your driver on that device. That means there's no runtime code. There's no co-installers. There's no setup EXEs. There's no MSIs. You have a manifest that defines exactly what's necessary for your driver, and that's the INF. With this design, we can target any type of Windows SKU. It can be an IoT device that must be installed completely offline by generating an image, or it can be giant, big Windows 10 Pro where everything can be done online and fluidly. But by having a declarative INF installation, you can target any system that Windows creates. Now you might say, I'm doing so many things with my co-installer. How can I actually do this? Well, one of the first things that we usually find is that there's some sort of applications or control panels being added with these co-installers. Instead of having this installed via the driver and the driver package, we want to move these applications into the store. By having them in the store, you have a very declarative application installation as well as a driver installation. By doing this, though, it means that your driver must be able to function completely without the presence of that app. Now, it doesn't mean you don't have the apps. It just means that the driver itself has all the information it needs to support itself. So take, for example, you have an awesome audio device, and it has an equalizer control panel. If that app isn't there, you should still be able to hear audio from your system. And this allows us to have a complete experience no matter what kind of Windows device you're on. If you put that audio chip on an IoT device, which doesn't have a screen, you can't have that app, but the driver continues to work and that audio still works. The other benefit you get from this is that if there's an app update necessary, you don't need to reinstall your driver. You just push a new app update through the store. So if I change my UI, I change a logo, today, if that app is part of the driver, you have to uninstall and reinstall the driver just to update the UI. It creates very, very unstable characteristics, and we want to avoid that. So we're going to remove that app from the driver package, and it's going to be installed from the store. So we have our app out of there. We no longer have our co-installer. We're all declarative. There's one more aspect that we want to tackle here, and that's to isolate the impact of the driver. Today, when a driver installs, it puts files all over the operating system. It puts registry keys everywhere. That makes it very difficult to maintain that driver. Because if I have two drivers and they happen to write the same registry key, we now have to try to figure out which one's the right entry. Is it the last one? Is it the first one? Is it the one that the user has changed? It makes it very difficult to maintain. So to avoid this, what we can do is we have all of the content for the driver installed relative to that driver. So for registry keys, that means using HKR rather than HKLM. So instead of putting it in the local machine directory, the registry hive, you put it relative to the driver. That means that if we uninstall, we can just take that whole directory, that whole registry hive, and remove it. Gone, clean, beautiful. The same is true for files. So with files, right now they're put into program files, system32, system32/drivers. All those locations have the same difficulty. Instead, we want to consolidate all the driver files and put them in one place. And ideally, that place is running from the driver store. And we'll talk even more about all these pieces in the lab tomorrow. Varaf and I will be there, and we'll go through a hands-on experiment here. For all these pieces, as you're testing and you're building, and you're like, great, I think I have a declarative driver. How do I know? Well, what's great is we already have a tool today called INF-Verif. It's part of the WDK, and you can use INF-Verif with a universal flag, and it'll tell you, yes, your driver is declarative, or no, and here's why. And it'll give you great error messages that'll specify, oh, hey, we found an old piece of code. This is no longer valid. Or, hey, we still see a co-installer here. You should remove that. And all these kind of things tell you exactly what you need to do with your INF to make yourself declarative. OK, great. So we've gotten a declarative driver. What's next? The next pillar we're going to talk about is componentization. Now, componentization, the goal of this is very similar to what we've done with Windows. We want to have a core base driver that works across any SKU you have. So whether it's IoT core or full desktop, that same core driver works and operates. And then layered on top of it are the customizations for each unique system that's used on. So why do we want to componentize driver packages? The reason we want to do this is we have today gigantic single monolithic packages. And these come down and they have information for a bunch of different systems or a bunch of different components, and a lot of it isn't necessary on most of the machines it runs on. Instead, we want to have it focused in, honed in, and targeted exactly for the information that the systems need. By doing this, it makes it much easier to produce bug fixes. If I have a driver today that I fork for each system that it installs on, I now need to maintain 4, 5, 10, 15 different copies of the same driver code, which makes it very difficult to make bug fixes and keep systems going as Windows updates and upgrades and continues. So instead, having a core base driver gives you a single code base that you can make fixes on, and it can then apply to everything that uses that code. And so everyone gets those benefits of those fixes, and it makes your time supporting all those systems much easier, much faster, much better. This doesn't mean we want to stop differentiation. That's extremely, extremely important. If you can't differentiate your device, then you're going to have a problem competing, and it hurts the whole ecosystem. So even if you have a base driver that works on all systems, you can also extend that driver to customize it and make it unique for a particular use case. So how do we do this? With Windows, with the Creators Update, we've added a functionality called Extension INFs. Extension INFs allow you to add customizations and special registry and system settings for a particular use. So in the case of this system here, we have one base driver and we have one extension. Both of those INFs apply to one device on that system, which means you have the base driver, which gives you the core functionality of the use. It gives you the basic audio coming out of your system. And then the extension would provide the tuning, the tweaks to make it perfect for the particular device it's installed on. And so this allows to fill the gap that also is being used by co-installers. So a co-installer would take a runtime component, it would execute during installation, and it would say, hey, which machine am I on? Am I on machine A or machine B? Depending on which machine it would be on, it would start tweaking settings. But this black box of operation we can't reproduce well when we're updating. Instead, you have an extension INF that's targeted specifically to a particular system. So to machine A, it would go to, or machine B, not both of them. And it would then set those particular settings based on a very clear, specific targeting, rather than runtime analysis. So the base INF contains all your common code, and your extensions contain all your specific bits for particular systems. Now, not all systems will need this. If you have a very simple driver, you have a mouse, you have a keyboard, I don't know, it may be that all you need is a base driver. All you need is the core functionality, and that's the same for everyone, and there's no customization, and that's fine. That's perfect. But if you do have customizations, you can then add an extension INF to deliver those customizations. So when you're creating an extension INFs are created just the same as any other INF. It's a text file with a .inf extension. It has the same familiar sections, the same familiar tooling, copy files, add reg, add service. All those things are supported in the same way. The only difference with them is that they are added after the base driver. So there's a special declaration that says, I'm an extension INF, and when we see that, we know that it gets applied after the base. So the base driver is installed first, then the extension INF. By doing this, you can then layer on those features, you can adjust functionality with that extension, and you can change defaults that might have been set with the base driver. And so you can have a base driver that works and functions everywhere, it comes with default settings, gets you off the ground, and then the extension comes in, tweaks that, and makes it perfect for that system. The beauty of this is you can actually independently service and maintain these. That means that the base driver can come from the IHV partner who creates the silicon. They say, here's my product, here's my base driver. And then an OEM or an integrator can take that, and they can add the extension INF on top. And each party can independently service those pieces. What does that mean? That means that if there's a bug fix in the base driver, the IHV can independently update that and maintain that. And if there's a change in the extension INF, the OEM has the ability to take that upon themselves. So let's say there's a typo in the friendly name. Instead of having to go through 4 or 5 different partners to make that happen, the OEM can do that directly. So let's take an example here. So we spent a lot of time. We had some partners come together. And this is an old, very complex model for an audio device that we started with. And you can see there are many layers, right? There's pieces of hardware, there are drivers from multiple different vendors. All of this was in one single package with all its private interfaces. And doing so made it extremely, extremely difficult to maintain. If any one of those pieces broke, the entire system stopped working. No audio came out of the system. So instead, we spent a lot of time, we analyzed that package, we broke it down, we said, how can we make this better? And this is where we landed. In this design, there are 3 base drivers. There's one for this DSP, there's one for the codec, and there's one for the APO. Each of the partners can now control, maintain, and process their own code and fix their own code. Before, they all had to communicate, and it all had to go through one pipeline to make this one giant monolithic package. But now we can break it up. The OEM extension in orange brings it all together. It has the customizations necessary for the APO and the codec in one place that the OEM can manage. And it allows us to say, okay, great. The codec comes down, that gives us the base audio functionality. It's extended with that extension INF. That brings in the APO, which has particular tunings, and the whole thing comes together in perfect harmony. Now, if something bad goes wrong, something breaks, someone goes out of business, audio will still function if you only have the codec. Nothing else needs to be there. Audio still works for that user. That means that support calls diminish greatly, because if there are problems, it can still sustain itself. But if everything's working great, all these pieces come together, and it gives you that very specific tuned solution that you're looking for. So that's componentization and declarative. Declarative is absolutely necessary for your universal driver. Componentization is optional depending on your design. And now we're going to transition to H, and I'll hand it back off to Varaf.
Thanks, Luke. All right. So the third important pillar of universal drivers are apps. So a lot of drivers may have companion apps associated with them. But again, as Luke mentioned earlier, these apps are optional to the function of that particular device or component. And if your driver has a companion app, we want that companion to be converted into a UWP app or a store app and be serviced and delivered through the store. So the state of the union today is all these hardware apps are written with Win32 APIs. The Win32 API means that a badly written app that might not take care of certain edge cases has a potential of bringing the user system down and may cause a blue screen. And this significantly impacts our users' customer satisfaction and increases the support call for our hardware vendors and for Microsoft. This hardware functionality and the Win32 apps are typically bundled within the driver package and installed using co-installer that Luke just referenced earlier. Since these apps are written referencing only Win32 API surface, these apps can only run on desktop. But what do you do with other Windows 10 editions like the Surface Hub and the IoT devices? How do we get an application platform and apps that work across all Win 10 OS editions? And UWP apps is the answer to that. We wanted UWP apps to work for hardware apps. So starting in Windows 10 Creator Updates, we made this possible by introducing custom capability. Custom capabilities are similar to other app capabilities that are already out there, like the general use, device, and restricted capabilities. So today, if you write a UWP app, you already declare these capabilities in your app manifest. Custom capabilities are nothing new in terms of how they are declared. Custom capability allows the capability owner, who is the owner of the driver or the NT service, to grant access to the driver or the NT service to specific apps. So this makes that app access very secure. Here is an example of how custom capability are declared in the app manifest. As you see, it's very similar to how other capabilities are defined. So the way a UWP app accesses custom capability, accesses a driver or an NT service through custom capability varies depending on whether it's an NT service or a driver. NT service access is lit up by using RPC. Traditionally, UWP apps don't have access to RPC endpoints, but custom capability essentially unlocks that access. For accessing drivers, we use the familiar Windows RT API, the windows.devices.custom, and that essentially allows UWP apps to access custom capabilities and through to the driver. So one of the questions that keep coming up is, can any UWP app access my driver or NT service? And the answer is no, not unless the capability owner explicitly grants access to those applications. Access is granted to applications by including a file called as a signed custom capability descriptor, or an SCCD, in the Apex. It's a very simple XML file. It contains a few elements. The first is the custom capability name, which the app is trying to access. Second is the app package family name, which is essentially saying that this custom capability is granted access to this app that is going to be signed with this certificate signature hash. And once this is created, this file gets essentially signed by Microsoft, so it cannot be tampered. Let's walk through a quick developer workflow. So a hardware developer wants to grant access to a specific app developer or an ISV to use their custom capability. The way they would do it is the hardware or developer or the capability owner will craft an SCCD, like we saw on the previous slide, for that app developer. The app developer will take the signed SCCD and package it in the Apex, and then publish the app to the store. As simple as that. And once the SCCD is included in the Apex and you declare the custom capability in your app manifest, you can use that capability like any other app capability. When a user tries to install the application, that's where all the security checks actually happen. So when the app is downloaded and installed, the operating system reads the custom capability and the signature to make sure that the app is who the custom capability or the SCCD file says it is. And only if all the security checks are passed, the app gets installed on the user's machine. If any of the capability checks fail, the app is not installed. So hence the trust model established between the hardware developer and the ISV. So any app will not be able to access somebody else's custom capability without their explicit permission. So as we were talking about custom capability and UWP apps to our hardware partners like yourself, we got this feedback saying that, great, you want us to separate apps from our driver packages and service these apps from the store. But how do we make sure the two come down together and there are version dependencies between the driver package and the app? How do we manage those? So in Windows 10 Creator Update, or actually in the Fall Creators Update, we are lighting this feature up. It's really straightforward. A driver package in the INF declares a dependency on the app PFN, and the Apex manifest declares a dependency on a minimum driver version. And the driver package then gets submitted to Windows Update, and then the Apex gets submitted to the Windows Store. The driver is always installed first, because as Luke mentioned, the device should be able to function without the app being there. So when the driver gets installed on the system, PNP recognizes that there is an app or a companion app associated with this particular driver. It then passes that information on to the Apex deployment handler in the operating system, which fetches the right version of the app. And when there is a version match between the min driver version that's specified in the Apex manifest and the one that's installed and the driver that's installed in the driver store, that right version of the app is installed. So all versions of the app are managed in the cloud. All versions of the driver are managed in Woo as well. So let's reiterate the benefits of hardware apps being UWP apps. Some of the benefits are germane to these apps being part of the Windows Universal Platform. They are designed to be written once, deployed to all Windows 10 devices, because the Universal App Platform is present in the one core OS. These apps, because they are UWP apps, have isolated impact, which I mentioned earlier. With Win32 apps, you did not have that. So the benefit to the end user is enormous. If an app is badly written or causes a crash for some reason, it will only bring the app down because the app is sandboxed in a container. App updates are easy to manage. They're deployed to the store, so you no longer have to make driver package updates just to update the app. And we already talked about the last two. Custom capability essentially allows these UWP apps to get access to drivers and NT services, and the version binding feature, which is going to be part of the Fall Creators Update. So we're here on our last pillar for universal drivers, is we want drivers to run on every single Windows 10 edition natively. And the way we do it is by writing your driver against one core UAP API surface. And when you build a driver just by targeting that API surface, since that API surface is present on every single Windows 10 edition, it makes that driver natively run on every single OS edition from now, and any new OS edition we may dream of in the future. An important point to call out is universal drivers come in all forms. We support KMDF, UMDF2, and WDM. Support for writing universal drivers has been present in the WDK since we first launched Windows 10 back in 2015. So when you switch your target platform to universal and build your driver, you're automatically linking against onecoreuap.lib, which means that your driver API surface is restricted to what's in the OneCore OS. We have a lot of samples, templates that allow you to build universal drivers. And they're all available today on GitHub, or templates come along in the WDK. Extensive documentation for how to write a universal driver, how do you verify a universal driver, is all present at aka.ms/universal Windows driver. So when you build a driver as universal, and you find out that you're calling into, let's say, kernel32.lib. So you may, if you come across errors, you have a few options. You first would have to switch your code to use substitute APIs. Substitute APIs are on MSDN, and so when you search for the old Win32 APIs, you will be able to find alternate APIs that are applicable to OneCore. In some cases, you may have to refactor your code and break the desktop-specific functionality out. Now, there is no guesswork in that because we have a tool that is run automatically when you build a universal driver in Visual Studio using the WDK called the API validator. It automatically checks whether your driver is calling into any API that is not within or not supported within OneCore UAP. So here is a sample output for API validator. If you look where the driver project OSR USB FX2 UM.dll, the DLL is linking against kernel32. And it'll tell you this is not allowed. So you have to go update to link against a DLL that's supported within OneCore UAP. The validation for universal drivers is no different than how we validate our driver projects today. I would encourage you to still continue using the rich driver tools that are available in Visual Studio that are delivered as part of the WDK, like your static driver verifier. Enable those tools, run those checks. It will flag any runtime issues that your drivers might see when you install them on a user system. In addition, we have highlighted two tools today which have been present in the WDK since the beginning of Windows 10. The API validator, which will essentially help you validate the U part of the universal driver pillar, and the INF verif. You use the /u flag to make sure that your driver is declaratively installed. The HLK content is available for desktop and for OneCore. And so I would encourage you to run HLK on desktop and IoT Core. IoT Core today is a representation of a OneCore operating system. The content for targeted towards IoT Core or a OneCore-based operating system is smaller than desktop because desktop HLK content has been growing organically for many, many years. We're just starting to get in the new OneCore-based content over the last 2 years. But every single OS release, we make a conscious effort to keep updating that list and adding more and more tests to make sure that we've got good coverage. And the Fall Creators Update is no different. Starting with in 2018, we'll also have additional HLK coverage that will help you validate your universal drivers to make sure that it complies with the D, C, H, and U principles that we have laid out today. And there's one more thing. So one of the benefits of universal drivers is we have a consistent set of APIs across all Windows 10 devices. So in Windows, we continuously make an effort to convert class-specific driver models, like how the NDIS driver model was in the past, and merge it into WDF, because there's a lot of benefits of writing WDF drivers, simplicity of code, power management, etc. So we're excited to announce that the newest edition of WDF in the Windows Creator Update supports the new NetAdapter class extension. This enables you to build a networking driver using WDF that a lot of you are already very familiar with. This is currently in preview, so I would encourage you to check out the aka.ms/netadapter that has videos, documentation, and also samples to help you get started. Another important point is the new NetAdapter class extension is in one core UAP. So when you write a driver for this device class, now you're universal from the get-go. So we've talked about a lot of different tools and how you would validate your DCHU. I wanted to put a roadmap of all the technology investments we've done. So the main point I wanted to drive home is everything that you need to write a declarative, componentized hardware support, write hardware support apps, write a driver that's universal API compliant, is all available today. So the universal API compliance is supported in the WDK starting the first Windows 10 kit back in 2015. In the creators update, we added support for hardware support apps, which is essentially custom capability allowing access for UWP apps to drivers or NT services. We also added support for extension INF that allows you to componentize your settings and your tuning parameters outside the core driver. So now you can have a common core driver and all associated settings and customizations can be serviced separately. We will continue to make enhancements and feature updates through Fall Creators Update and through the next spring release that will make this that will make it better, provide you better validation, provide you better documentation and samples. And also the HLK submission enforcement, as we heard in the Windows 10s conversation, that is something that's going to be happening in 2018 as well. So based on the audio pilot that Luke talked about earlier, we decided that it would be helpful to put together a quick workback schedule of how long did it take for us to go convert the audio driver, which was pretty complicated, to be declarative, componentized, and have a hardware support application. So here is a quick workback schedule. The call to action for everybody is to start by running inf-verif/u, which is in the WDK, on your drivers. This will give you a good indication of where is your driver not ready to be declaratively installed. And then you can have a good roadmap, and you'll have some time on addressing these issues, and then testing these issues and continuously running the INF verifier to make sure that by the time you get to 2018, your driver project, your application, if you have one, is ready to meet the new requirements and also to participate in this Windows ecosystem of making Windows more resilient to upgrades and making your drivers more resilient to installs, uninstalls. So I wanted to thank everybody for joining us today and giving us the opportunity to share with you Microsoft's guidance, timelines on transitioning to universal drivers. As I mentioned earlier, the time to start is now. Technology is not a barrier. You have all the tools that you need in the WDK to get you started on that journey. Universal drivers, as we highlighted today, will improve driver quality, and it will make OS updates and driver updates a lot more resilient. It will also contribute to our end user customer satisfaction and by allowing them to stay current. So Windows is releasing updates at a tremendously fast rate. We want our users to get those updates as soon as they are released. And we know it's very expensive to keep drivers up to date if we stay course on the old way of doing things. We have to adapt. We have to change. Some of the timelines for universal driver enforcement, and I want to echo what you've already heard in the previous session on Windows 10s. Starting with Windows 10s Fall Creator Update, net new systems will need to be DCH compliant, which means that your drivers need to be declaratively installed. If you have OEM customizations and settings, they need to be abstracted out by using extension INFs. And if you have a companion app, you should move that to the store. In February 2018, this requirement gets to be even broader, where it's not just for Windows 10s, but it's for all net new systems that are shipping after that point. Sometime in summer of 2018, we will have enforcement for all four pillars: declarative, componentized, apps in the store, and universal API compliance. As I mentioned earlier, the tools are available to you right now. Partner with your Microsoft contact if you have any issues or questions, and we want to get everybody updated, and we want everybody to experience the benefits of universal drivers by keeping the customers current on the latest OS. We have a lot of documentation and samples. In fact, we just published a nice how-to guide on universal drivers, which is essentially a compilation of all the documentation, samples, and we're going to add even how-to videos that we have created over the past couple years that walk you through these different steps. That's available today as well. We encourage you to attend all the driver sessions after lunch because it's a story that we are saying. Luke and I just talked about the principles and pillars of universal drivers. You'll hear about other updates in how you flight these drivers to know the real-world quality impact of your drivers before you release these drivers publicly. And there are other sessions on driver servicing, quality, and dev center updates, so be sure to attend that. Also, we would encourage you to attend a lab that Luke and I are hosting on day 2 tomorrow, which will walk you through end-to-end of how do you build a driver that's declarative, componentized, how do you write a UWP app that talks to a driver, and how do you package everything up so that it can be serviced and updated resiliently. So at this point, I want to thank everyone for attending our session today, and please enjoy your lunch.
Thank you, everyone.